James Webb, once again, requires scientists to rethink our understanding of the universe. In the latest discovery, the telescope has just detected a key building block of life at the dawn of the universe, upending what we know about the first galaxies. The discovery, a cloud of carbon in a distant and compact galaxy as it appeared just 350 million years after the Big Bang, marks the earliest detection of an element other than hydrogen in the universe. The results have been accepted for publication in the journal Astronomy and Astrophysics, and a preprint version can be found on AR-Archive. As co-author Roberto Maiolino, a professor of experimental astrophysics at the Kavli Institute for Cosmology at the University of Cambridge, said in a statement, "Earlier research suggested that carbon started to form in large quantities relatively late, about 1 billion years after the Big Bang. But we found that carbon formed much earlier. It might even be the oldest metal of all." Astronomers classify elements heavier than hydrogen and helium as metals. That's because, aside from hydrogen and trace amounts of lithium, these elements were forged inside the fiery furnaces of stars and distributed throughout the universe by star explosions called supernovas. This process of heavy element production and seeding was once thought to take many star lifetimes before elements heavy enough to form planets were widely available. But new discovery made by James Webb has challenged this preconception. What James Webb found in the remote galaxy known as GSZ-12, which was 100,000 times less massive than the Milky Way, were traces of oxygen and neon mixed with a strong signal of carbon. Exactly how carbon could have formed so early in the universe's life is unclear, although it could be due to stars collapsing with less energy than initially thought, according to the researchers. As carbon would have formed in the star's outer shells, this could have enabled it to escape and seed the early universe sooner than expected, instead of being sucked inside the black holes formed from the collapsing stars. That means it's not necessarily true that life must have evolved much later in the universe. Perhaps life emerged much earlier. Perhaps somewhere, under some conditions we might even consider too exotic for life, there are living creatures completely unlike us, better suited to surviving, thriving, and building an interstellar civilization in the cosmos. Perhaps they're not made out of familiar ingredients like proteins, but something else entirely, like a crystalline or metallic set of structures. At that point, it simply becomes a game of hide and seek. Where is everybody? Why haven't we made first contact with aliens yet? This question is known today as the Fermi paradox, and it has had astrobiologists and other scientists scratching their heads for ages. First off, if we want to understand how the universe makes intelligent life, we have to consider two things. First, we have to consider the steps that needed to occur in order to bring about our own existence. And then, we need to think about ways that intelligent life could arise in circumstances that differ from our own, and to make sure, wherever possible, that we're doing it in as quantitatively accurate a fashion as possible. We also have to make sure that we don't make unfounded assumptions or fall for any one of a number of logical fallacies, like conflating absence of evidence with evidence of absence, or the post hoc ergo propter hoc fallacy. It's also important to learn how not to estimate what's out there. There are two all too common mistakes that people, even the most brilliant of scientists, make when considering this question. One is that they make point estimates akin to, "We may not know this parameter, so here's what we estimate it to be," which is relatively meaningless. If you're going to make such an estimate, it's only meaningful if you include an uncertainty range, a set of error bars, or some other likelihood predictor. There's an enormous difference between saying that you estimate the odds of something to be 1 in 100 with a 10% uncertainty, a 1,000% uncertainty, or a two-tailed uncertainty, where it could be as high as 1 in 10, but there could be no lower limit at all. However, the other mistake that people make is perhaps the most common of all when it comes to attempting to answer the Fermi paradox, making use of the Drake equation. The Drake equation yields many interesting lessons, and when it was first put forth, it was a monumental achievement from a scientific perspective. For the first time, it broke up a seemingly unknowable question of how many intelligent, spacefaring civilizations there are within our galaxy today into a series of smaller questions that we could conceive of solving one at a time. For example, we could measure or estimate things like the rate of star formation in the Milky Way, the share of stars that have planets, the average number of potentially life-supporting planets around stars with planets, the fraction of planets that could have life that actually wind up with life, the fraction of planets with life that go on to develop intelligent life, the fraction of intelligently inhabited planets that emit detectable signals, or the length of time that such civilizations continue to emit those signals. When you multiply all of those things, you'll wind up with an estimate for the number of active civilizations that we could potentially detect today. But immediately, we run into a few major problems. For one, we've measured the rate of star formation in the Milky Way, and we actually know it pretty well. Unfortunately, if you took that star formation rate and multiplied it by the age of the universe since the hot Big Bang, you'd wind up with almost no stars. You'd calculate that the Milky Way should have formed a total of around 10 billion stars over our cosmic history. I know that 10 billion probably sounds like a big number, but compared to the actual estimate for the number of stars in our galaxy, which is more like 400 billion, it's only 2 to 3%. Fortunately, it's easy to identify why this method of calculating how many stars we've formed, which you'd imagine would give you the total number of stars in the galaxy, is so thoroughly wrong-headed. The superficial reason is fairly obvious. The star formation rate is not constant over our cosmic history. In fact, we've come to understand that the universe was born without stars, which began forming during the first 200 million years or so. We've learned that star formation increased for the first 3 billion years of our cosmic history, reached a peak, and has been dropping ever since. Locally, we've probably experienced bursts of star formation when we've absorbed smaller satellite galaxies. And we might even be starting to experience another burst as the Magellanic Clouds and Andromeda exert their gravitational influence on the gas, dust, and other neutral matter within our own galaxy. But that's only the superficial reason why the Drake equation is problematic today. The deeper reason is that the Drake equation, when it was put forth, made an assumption about the universe that we now know is untrue. It assumed that the universe was eternal and static in time. As we learned only a few years after Frank Drake first proposed his equation, the universe doesn't exist in a steady state, where it's unchanging in time, but rather has evolved from a hot, dense, energetic, and rapidly expanding state. A hot Big Bang that occurred over a finite duration in our cosmic past. Instead, a much more productive route is to calculate the quantities we now can speak about with some level of certainty, and then move on to the great cosmic unknowns in as responsible a fashion as we can. Unlike the situation some 60 years ago, when the Drake equation was first proposed, we now have an excellent idea of what our universe is like, both in and beyond the Milky Way and the local group. We understand what the various populations of stars are that exist, and what sorts of steps need to occur to make heavy elements, rocky planets, and allow for the possibility of complex chemistry and important reactions, such as the formation of energy-storing molecules from nothing more than the ubiquitous building blocks and starlight. We've also learned a lot about the types and abundances of planets that exist around stars other than our own, exoplanets. As recently as 30 years ago, we were only discovering our very first planets around stars besides the Sun. At the end of 2021, we're closing in on a whopping 5,000 confirmed exoplanets. And sure, there are biases in our data. We're preferentially detecting the planets that are the easiest to detect. But we know how to account for those biases. Instead of needing to speculate about how many stars form, how many have planets, how many planets per system have the potential for life, we can actually utilize some excellent data. Here in our modern Milky Way, we already know how many stars there are, how those stars are divided into different populations, how many planets there are per star, how many of those planets have the right composition of elements to lead to complex chemistry, and how many of those planets have the potential for hosting life. On this front, it's actually straightforward to come up with a solid estimate for how many potentially habitable planets are in our galaxy. In fact, we can perform that calculation in a variety of ways, just to show the power of our set of knowledge. Of the approximately 400 billion stars in the Milky Way, about 80% are red dwarfs, or 18% are like the Sun, and only 2% are too massive and short-lived to be interesting for life. As far as we can tell, there are about 5 to 10 planets per stellar system, with approximately 1 to 2 planets in what we call the habitable zone around each star. Of the planets that exist around Sun-like stars, we believe that 20% of them are Earth-like in terms of size. A greater percentage than that are terrestrial around the more common red dwarf stars. If we assume conservatively that red dwarf systems are not habitable at all, but Sun-like systems are, then all we have to do is multiply the following figures. The number of stars, 400 billion. The proportion that are Sun-like enough to support life, 0.18. The number of expected potentially habitable zone planets per relevant star, 1.5. The fraction of those planets that are Earth-like in size, 0.20. We then derive an estimate for the number of potentially inhabited planets in the Milky Way, 21,600,000. It doesn't make sense to use so many significant figures. 20 billion is good enough. But also, we have to remember that all of these numbers have uncertainties. There may be as few as 200 billion stars, half of our estimate. Some of the stars may be too low in metals, what astronomers call the heavy elements in the universe, for planets to support life, but the percentage is small, less than 10% for certain. Some stars might not have planets, but again, the percentage is small, less than 20% for certain. The habitable zone may be larger or narrower than we think. Tack another 33% uncertainty onto our estimate. And we haven't sampled the low end of the mass radius portion of the exoplanet population very well. Our estimate of 20% being Earth-like in size could go up or down, so it's reasonable to put a 25% uncertainty on that figure. All in all, there could reasonably be as few as 5 billion potentially habitable planets in the Milky Way, or perhaps as many as 50 billion. If red dwarf systems are potentially habitable as well, that number could increase tenfold. And at the same time, many of the things we've worried about in the past likely don't particularly matter one way or the other, such as whether a planet has a major moon or not, whether it has a Jupiter-like world in its stellar system, whether it's located close to or far from the galactic center, and whether it's a part of a singlet or multi-star system. But beyond that, we still have some major unknowns where our level of cosmic ignorance is truly staggering. We know the ingredients that life requires are ubiquitous everywhere we look. In asteroids, in gas in the galactic center, in outflows around massive, newly forming stars, and even in the atmospheres and on the surface of other planets and moons in our solar system. But even with all the raw ingredients, what is the fraction of potentially inhabited planets where life actually arose from non-life? In Carl Sagan's original Cosmos series, he gave a figure of 0.10%, and asserted that this was a conservative number. That is not necessarily the case. Life could be difficult. Just because it arose early in the history of Earth doesn't mean that a significant fraction of planets actually have or ever had life on them. It could be nearly 100%, or 10%, or 1%, or 0.01%, or a 1 in a million chance that life arises from non-life. So if we rewound the clock and started Earth over again, how likely is it that life would have arisen and thrived here? Well, our ignorance is astounding. Similarly, once life does arise, how often does it get wiped out, versus how often does it endure for many billions of years? How frequently does it remain in a relatively simple state, unable to develop complexity, differentiation, multicellularity, or sexual reproduction? How often, even after billions of years, does it actually begin to look like life on Earth at the start of the Cambrian explosion? Again, we have no knowledge at all about how this might work. If you estimated that it occurred 10% of the time, that's reasonable. But so is 90% of the time. So is 0.001% of the time. Without observational or experimental evidence to point us in the right direction, we're simply deluding ourselves if we make a strong assertion. Furthermore, we know that after life on Earth became complex, differentiated, multicellular, and sexually reproductive, it still took more than 500 million years for a species to arise that would become technologically advanced, and that was likely just the result of random chance. How often does that occur? Does it make sense to represent this probability in percentages, or is this such a rare event that it's like winning the Powerball lottery 5 times in a row? Furthermore, how long does that technologically sophisticated life endure? Does it ever become a multi-planet or even an interstellar civilization, or is the progression from technologically advanced to extinct a relatively rapid one? At this point, our uncertainties are so large that it's eminently reasonable that not only might human beings be the only intelligent life in the Milky Way, but in the entire observable universe, which likely contains more than 1 trillion times as many stars as our own galaxy. We can confidently say, give or take, that there are perhaps 20 billion Earth-sized planets made of similar elements to our own world, at the right distance from their parent star to have liquid water on their surface, assuming an Earth-like atmosphere as well. But of those worlds, how many of them have life? It could be most of them, many of them, or only a tiny fraction. Of the ones with life, how many of them develop complex, differentiated, intelligent, and technologically advanced life? Before we even start asking questions about longevity, colonization, or machine-based life, we should admit, with a non-negligible probability, the most obvious resolution to the Fermi paradox. The reason we haven't made first contact with intelligent, technologically advanced, and spacefaring alien civilizations is because there are none. In all the galaxy, and perhaps even in all the universe, we really may be alone. Without evidence to the contrary, we have every reason to keep looking and searching, but still no reason other than our own preferences to believe that other creatures, similar to humans, exist out there. While it may be incredibly fun to theorize a myriad of possible explanations as to why intelligent extraterrestrials might remain hidden from us, the simplest possibility, that they just aren't out there, should be the default hypothesis until proven otherwise. What's notable, in addition to upend what we know about life in the universe, James Webb is also providing science with a further gift. Detecting exoplanets used to be so difficult that scientists spotted the first black hole, detected the leftover radiation from the Big Bang, and took snapshots of countless distant galaxies before discovering the first planet beyond our solar system in 1992. Plenty of exoplanet astronomers began their careers before the field of exoplanet astronomy even existed. But now, astronomers have identified well over 5,000. And continue to find more. Given the stream of discoveries, it can be easy to forget how little we still know about these distant worlds. The colorful volcanoes, oceans, and cloud-streaked atmospheres that appear in artists' renditions are speculative fantasies often inspired by the only information scientists have about most worlds: their mass, radius, and distance from their star. But the James Webb Space Telescope is revealing exoplanets in dazzling new detail. Scientists are using the telescope, launched at the end of 2021, to study the atmospheres of hundreds of worlds, from gas giants to rocky worlds about the size of Earth. As an exoplanet orbits its star, starlight passes through the planet's atmosphere, and light at specific wavelengths is absorbed depending on the gases present. This leaves traces in the spectrum of starlight, which scientists can use to figure out which chemicals the light passed by. James Webb is sensitive to infrared wavelengths where these traces are strongest and has already detected water, carbon dioxide, methane, and more on other worlds. That means Webb's planned 10-year lifetime could reveal a lot, perhaps answering fundamental questions including what exoplanets are made of, how they form, and whether our solar system is an oddball within our galactic neighborhood. Here are 5 big planetary puzzles that scientists hope to solve with James Webb. 1. Why do some rocky planets have atmospheres and others don't? If a rocky planet is going to host life, it needs an atmosphere. But scientists still aren't sure what determines whether a rocky body can hold on to a gaseous outer shell. Astronomers are searching for what they call the cosmic shoreline, a conceptual dividing line that separates worlds with and without atmospheres. In 2017, scientists identified such a shoreline within our solar system, set by the balance between the amount of radiation a planet or moon receives from the sun and the strength of the world's surface gravity. Sunlight provides gas particles with the energy needed to escape from the upper atmosphere, while gravity holds atmospheric gases to the planet. To test whether this type of cosmic shoreline exists throughout the galaxy, scientists need to figure out which exoplanets have atmospheres and which don't. This question may sound incredibly basic, but it's only just now becoming possible to answer thanks to James Webb. Renyu Hu, an astronomer at NASA's Jet Propulsion Laboratory in Pasadena, California, says he and colleagues have settled the atmosphere question for 55 Cancri E, a planet that orbits a sun-like star some 40 light-years from Earth. 55. Cancri E is a super-Earth, a bit bigger than Earth but much smaller than Neptune. In a paper published May 8 in Nature, Hu and colleagues present Webb's data, suggesting that 55 Cancri E has an atmosphere of either carbon monoxide, carbon dioxide, or a mix of the two with nitrogen. It's the first detection of an atmosphere shrouding a terrestrial or rocky exoplanet. But scientists are pessimistic about the existence of atmospheres on the other rocky worlds James Webb is observing, specifically those orbiting M-dwarf stars. These small, dim stars are easiest for James Webb to see. They also tend to spew bursts of atmosphere, stripping radiation more often than stars like our Sun. So some scientists doubt that rocky planets around these stars can hold onto atmospheres. According to James Webb observations of LHS 3844b, a super-Earth orbiting such a star, the planet is almost certainly a bare rock. Webb's observations of the planets TRAPPIST-1b and TRAPPIST-1c, which orbit the M-dwarf TRAPPIST-1, suggest that these planets are bare too. But it's also possible that they could have very thin atmospheres, says astronomer Elsa Ducrot of the Paris Observatory. Follow-up work with James Webb will help settle the question. As scientists use the observatory to identify more examples of rocky planets with and without atmospheres, our understanding of the cosmic shoreline can be put to the test. 2. What is exoplanet geology like? Discovering exoplanets without atmospheres also will allow astronomers to study something impossible to probe directly before James Webb: exoplanet geology. Scientists plan to use James Webb to look for the chemical fingerprints of specific rocks in the infrared light cast by the rocky, airless super-Earth LHS 3844b. Learning what the planet's surface is made of would be a powerful clue about the planet's geologic history and ongoing processes. Finding signs of granite would be especially intriguing. Granite is a common rock on Earth that forms from recycled and remelted rock. On Earth, this process depends in part on plate tectonics. But beyond Earth, granite appears to be vanishingly rare, probably because plate tectonics is too. Right now, there's no more evidence for plate tectonics on other worlds than there is for alien life. Thus, finding granite-like rock on an exoplanet would be a major discovery. 3. What are rocky exoplanets made of? While James Webb will help astronomers learn about the surfaces of exoplanets, it also might offer a glimpse at their geologic guts thanks to a particularly extreme type of terrestrial world. Hotter than scorched Mercury, lava worlds orbit so close to their stars that their years are best measured in hours, not days or months. This proximity causes the planets to become tidally locked, meaning the same side of the planet always faces its sun. As a result, one hemisphere freezes in endless night while the other's rocky surface melts into lava. The magma oceans on the day sides of lava planets offer about as close to a window into the interior of a planet as astronomers could hope to find. Gases escaping from the magma might give clues to the composition of the planet's deep interior, and learning what planets are made of can tell astronomers a lot about how these bodies form, and whether their compositions and histories are similar to or different from the way rocky planets form in our solar system. 4. Sub-Neptunes are the most common planets in our galaxy. What are they? While what we know about Earth, Mercury, and Mars can help astronomers imagine what alien rocky planets are like, the most common type of planet in our galaxy can't be found in our solar system. UB Neptunes, so named because the planet's radii are just a bit smaller than Neptune's, seem to be everywhere scientists look. But scientists still know very little about these worlds. For example, are they gas giants, rocky planets, or something else entirely? Based on their masses and radii alone, sub-Neptunes might be miniature ice giants rich in ammonia, methane, and water, like Neptune and Uranus. But the same data could describe planets with very different structures, such as rocky cores wreathed in hydrogen and helium, or exotic water worlds made mostly of different forms of water, not necessarily liquid. Using James Webb, scientists plan to study the atmospheres of sub-Neptunes to distinguish between these possibilities. Webb's observations of the sub-Neptune K2-18b made headlines last year after researchers detected carbon dioxide and methane, but no ammonia, an expected component of gas planets, in its atmosphere. The team interpreted this gas mix as evidence for a water world, since ammonia dissolves easily in water and would get trapped in an ocean if it were there. But other researchers think the same data could fit a Neptune-like composition with a thick gas envelope over a rocky core. A definitive answer will require follow-up observations. 5. How do gas planets form? Despite having 4 gas giants in our solar system, scientists still aren't sure how these enormous worlds form and evolve. How do gaseous planets form? How do they evolve? And what are they made of? These are fundamental questions in planetary science that scientists still haven't answered. In particular, scientists want to know whether gas giants form where we find them, or whether they tend to wander over time, as they seem to have done in our solar system. Planets can wander due to gravitational interactions with other objects, including the disks of gas and dust that orbit young stars and provide the raw materials for planets. Gas planet migration can wreak gravitational havoc, knocking other planets out of their orbits and flinging around small bodies like comets and asteroids. The resulting chaos can have serious implications for the stability and potential habitability of smaller worlds. James Webb could provide astronomers with a vital clue to this mystery: the composition of gas giant atmospheres. The abundance of elements heavier than hydrogen and helium in gas giant atmospheres should depend on where the planet formed relative to its star. In general, the heavier the elements found in an atmosphere, the farther out the planet formed. Observing enough gas giant planets to start identifying trends, and planets that buck them, could reveal the general rules governing how these planets form and migrate. That's all the information that we have for you today. Don't forget to give us a thumbs up if you enjoyed today's episode, subscribe if you haven't already, and hit the bell so you never miss out on future episodes. And be sure to also tell us what you think about today's content. Everyone's support motivates us to continue delivering quality content and to always improve. As always, thanks for watching, and we will see you next time.